An interstellar object zipped past the Martian sky faster than expected. It was October 2025. The Perseverance rover's evening cameras recorded a surprising burst at 60 kilometers per second, aligning perfectly with the velocity and schedule of the groundbreaking Interstellar Visitor 3, known as I/Atlas, during its close approach to Mars. Planned satellites around the red planet suddenly lost signal, and the unedited photos disappeared without a trace. Soon after, unverified accounts emerged of several swift entities and an enigmatic emerald glow, leaving experts on high alert. Initial snapshots from the Mars pass suggested irregularities, actions that no typical comet would exhibit, coupled with delays in official disclosures right when explanations were crucial. What secrets lay hidden in those absent shots? Might these hints reshape our understanding of objects from beyond our solar system? On October 2nd, 2025, Stephen Burns, a prominent name in backyard stargazing circles, shared a 9-minute time-lapse of the night view pulled from Perseverance's unprocessed image library. Compiled from a series of back-to-back exposures, the footage reveals a razor-sharp line slicing through the starry Martian backdrop. The evident speed of 60 kilometers per second grabs attention right away, outpacing any familiar shooting star, orbiting craft, or radiation glitch usually spotted in rover recordings. To put it in perspective, NASA's Parker Solar Probe, humanity's quickest creation, hits 192 kilometers per second, but only near its closest solar swing, pulled deep into the sun's pull. In this instance, the line maintains a constant velocity far from the sun at Mars's orbit, a rate usually linked to travelers from interstellar space. Burns approaches his work with precision. He aligns the unprocessed images over a stable stellar map, adjusts the field scale via established star gaps, and verifies timing across each shot for accuracy. The line's path gets tracked against the fixed stars in every frame, eliminating possibilities like stationary lens flaws or particle impacts. By fixing missing segments and verifying against available celestial diagrams, he releases the complete set and encourages fellow enthusiasts to verify or debunk it. The discovery spreads like wildfire online. Thousands grab the files, reprocess the layers, and argue if the line is genuine, a glitch, or perhaps even more unusual. Burns's track record in detailed analysis and doubt lends credibility to his reveal. He stresses the importance of outside verification, warning against jumping to wild theories until the line's source gets solidly proven by others. The math checks out. Should the 60 kilometers per second figure prove solid, the trajectory lines up spot on with the forecasted path of I/Atlas across the sky. Yet the onus now falls to the wider group. Will hobbyists confirm the oddity, or will it fade away under deeper examination? Discussion boards explode the moment Burns's time-lapse hits the web. In mere hours, countless solo reviewers snatched the Perseverance shots, keen to recreate or refute the 60 kilometers per second line. Opinions split fast. A few achieve results, layering the exposures with tailored programs. They assert seeing not only the primary path, but traces of additional quick blurs in the October 3rd batch. Counterparts using different methods detect only static. Charges of data manipulation and flaw chasing bounce around. At 00003 UTC, a short verdant burst shows up in one team's video clip. The tiny pixel irregularity sparks waves of conjecture. Does it represent an actual light release or merely a radiation hit boosted by intense processing? Competing groups break down the hues, clashing over adjustments and lens options. Proponents argue the green burst fits chemically, like a comet's spectral signature. Skeptics reply that Mars's sparse air and the imager's tech traits make such bursts more prone to being sensor echoes than true events. The shortage of pristine, untouched files heightens the doubt. Lacking the base data files and sensor logs, all assertions remain tentative. Evaluations of noise levels, shot-to-shot stability, and particle filtering turn into hotly contested areas. No prompt official data drop, no quick analysis tools, no setup guides stoke doubts further. Is this standard delay for dynamic observation efforts, or a calculated holdback? Tensions rise in the enthusiast circle. Certain voices call for agency intervention, pressing NASA or ESA to step in and resolve the method debates. The rest commit to collaborative tools, uploading scripts and partial assemblies to foster group confirmation. The oddity's existence teeters uncertainly, its outcome now linked to if future Mars satellite efforts provide clear, self-checked visuals. For a short period in early October, Mars served as the prime solar system spot to observe an extrasolar guest. 3 satellites, MRO equipped with HiRISE, ESA's Trace Gas Orbiter with Cassie, and Mars Express featuring VMC, were assigned to image it at 3/9 million km away, roughly 75 times Earth's lunar separation. Such an immense gap means even Mars's keenest lens, HiRISE, would render the intruder as barely a blur. Its optimal clarity would barely. Instruments scaled to dozens of kilometers per pixel. The high-resolution imaging science experiment, HiRISE, crafted to detect rocks on Martian hillsides, had never targeted anything shifting at such velocity or distance. Its capture routines were adjusted for the close approach with fresh orbital data, directing the tight viewing angle just beyond the forecasted route. Every shot represented a risky bet. Position it prematurely, and the target slips from sight. Delay it, and it merges with the stellar backdrop. The Color and Stereo Surface Imaging System, CASIS, optimized for chromatic scans and plume studies, set up a sequence of 4 wavelength shots, aiming to capture the core along with any debris or streams following it. The high-resolution stereo camera, HRSC, on Mars Express, featuring a broad sweep and multiple spectral channels, took on the job of probing rough outlines. Might it separate a lone core from a grouping or detect a solar wind plume amid the brightness? The effort demanded exacting teamwork. Observation schedules for each satellite relied on exact forecasts from JPL's Horizon system, refreshed each day as the path of 3I/Atlas sharpened. The probes had to pivot from their standard nadir orientations, occasionally by a few degrees, to follow a tiny wanderer through the vast cosmos. Onboard constraints ruled out live following. Each photo was a fixed moment, relying on the precision of final-hour computations. For items at vast solar system spans, a slight flaw in the orbital info could spell complete failure. As the encounter neared, sensor groups balanced clashing demands, extending capture durations, reducing interference from cosmic rays, and carving out vital data links for swift transmission. Each picture faced intense examination for signs of form. Was 3I/Atlas a unified chunk, a scattered pile of pieces, or an even odder entity? From this distance, only traits spanning tens of kilometers would appear. Spectral filters, if obtained, could expose material clues like wide emerald, azure, or crimson bands suggesting unusual makeup. The risks loomed large. With ground telescopes overwhelmed by sunlight, the Martian satellites offered the sole unobstructed view. The goal remained straightforward. Should peculiarities arise, splitting, outflows, escorts, these visuals would reveal them first. The whole operation pitted against layout, speed, and the clock. No unprocessed visuals. That mantra resounds through all talks as hours pass post-Mars pass. Typically, data from Mars satellites, particularly from major occurrences, reaches open repositories shortly after receipt, even if raw. Here, 0. Nothing from HiRISE, nothing from CASIS, not even the standard preview shots from Mars Express. The quietude is total, interrupted solely by mission reports alluding to continued adjustments and checks. Within JPL, the photo specialists confront another form of strain. The issue goes beyond data limits or red tape. It involves the danger of sharing images peppered with particle strikes, unflagged faulty pixels, or jumbled overlays that might pass for true debris or plumes. For a swift passerby like 3I/Atlas racing the heavens at 60 kilometers per second, usual processing chains falter. Background leveling, shape fixes, and brightness tuning all require overhaul. Even top-tier filters for rejecting cosmic rays, calibrated for sluggish Martian terrain, falter in distinguishing a true interstellar trace from a rogue ion. JPL's photo director, amid mounting outside gaze, likens the effort to a contest with flaws and hopes. Each shot demands verification of alignment shifts. Did the forecasted orbit match the real heavens? Did a ray or sun bit create a fleeting mark that could mimic an attendant? In this setup, even layering photos, a standard procedure, turns hazardous. offset by a sliver, and illusions proliferate. Layer 2 forcefully, and subtle authentic details fade. The consequences stand evident. Share hastily, and a false signal might spark worldwide uproar. Linger excessively, and claims of concealment grow. The adjustment crew advances image by image, matching estimated movement to visible pixel paths, marking irregularities for hands-on inspection. Each potential shard, each strange glimmer enters records, sparks arguments, and gets resolved or elevated. No one at JPL pretends the holdup feels good. The truth lies in a logjam of prudence, favoring reliability over haste. While the globe anticipates, the upcoming drop must address far beyond interest. It has to resolve through proof whether Mars' lenses snagged a solitary core, a debris assembly, or an anomaly calling for fresh theories. A comet's verdant shine viewed from millions of kilometers distant typically wraps up neatly. Dicarbon or C2 releases a vivid green mark as solar rays sever its ties, a method so dependable that seekers rely on it as a molecular badge. For 3I/Atlas, though, the narrative complicates. Reports from observers from the Mars flyby period report a brief green burst spotted at 0003 UTC within certain Perseverance image sequences. The conclusion is straightforward. Should the burst prove authentic, it would indicate the presence and activity of dicarbon in the coma. Yet initial tentative analyses from Mars Express and TGO suggest otherwise. The typical C2 emission features appear faint or entirely absent, supplanted by a composition heavy in carbon dioxide and light on traditional carbon compounds. In laboratory contexts, a green glow devoid of dicarbon represents an impossibility. Conventional astrophysics struggles to account for a spectrum that radiates green without the characteristic Swan bands at 516 and 563 nanometers. If the hue is legitimate, it calls for an alternative process or an unidentified substance influencing the outcome. Experts in spectroscopy, accustomed to debunking misleading signals, recommend restraint. Absent precisely timed, calibrated spectra aligned with the alleged burst's instant, the compositional inconsistency stays unexamined. Could the green have been an authentic radiative occurrence, or merely a glitch arising from image processing and hue adjustments? Only the forthcoming unprocessed data from Mars satellites can clarify this discrepancy through instrument-confirmed spectral readings. Upcoming data publications must demonstrate, on a pixel-by-pixel basis, if 3I/Oumuamua's makeup truly defies established norms. The spectral findings from the Mars mission pose a direct test to conventional comet studies. Preliminary insights from the Mars Express group emphasize an emission profile led by nickel rather than iron, flipping the pattern seen in solar system comets. Normally subdued or overshadowed by iron, nickel signatures now dominate the display. Scientists scrutinizing the elemental proportions observe that no baseline accretion theories foresee this dominance hierarchy. The irregularities extend beyond heavy elements. The trace gas orbiter's sensors detect a gas blend where CO2 release vastly exceeds water vapor by a factor of 10. For a solar-approaching comet, H2O ought to dominate. Instead, CO2 reigns supreme with water scarcely detectable. The jet patterns add further twists. Imagery from Mars orbiters, despite their coarse resolution, reveals a stream not extending sunward but surging ahead, an anti-tail, sunward pointing, and distinctly edged. This ejection drops away so abruptly that dust simulations fail to replicate it adequately. The usual expansive, fan-like tail is nowhere to be seen. Rather, the stream's forefront is sharp, with an implausibly abrupt decline in intensity. Modelers employing fluid dynamics computations conclude that just a substantially massive, compact core could maintain such a configuration without disintegrating or veering off trajectory. Orbit trackers assess the body's heft by monitoring deviations from pure gravity, subtle pushes from outbursts, or asymmetric venting. For 3I/Oumuamua, observations yield no such perturbations. Despite evident jets, its trajectory adheres closely to the forecasted orbital path. This suggests a minimum mass exceeding 10 billion tons, more akin to an asteroid than a comet. Investigators catalog each peculiarity, discuss it vigorously, and compile them into an expanding file of enigmas. Explanations drawn from natural processes strained to encompass the chemistry, the motion, and the enormous scale. Tension builds as experts ponder if these traits merely revise comet doctrines or hint at an entity beyond natural origins. Avi Loeb, renowned for challenging frontiers in interstellar studies, joins the conversation with a bold assessment. His collaborators execute trajectory projections, tracing 3I/Oumuamua's course backward over years to check for alignment with the iconic 1977 WOW signal. That 72-second radio pulse at 1,420 MHz, the neutral hydrogen frequency. Leveraging JPL Horizon's data and Monte Carlo methods, they pegged the probability of this positional match at roughly 0.6%. Uncommon, yet feasible. The hydrogen frequency carries particular significance in SETI discussions, as it's the band prime for extraterrestrial transmissions. Loeb's colleagues contend that any candidate warranting dedicated radio scrutiny is one traversing the WOW locale at interstellar velocities. SETI specialists, ever prudent, highlight the dangers, location ambiguities, the sky's immensity, and the temptation of hindsight bias. Nonetheless, the precision of a narrowband hydrogen emission stands as the benchmark for non-natural origins. Nature avoids such focused broadcasts. Now with 3I/Oumuamua occulted by the sun, uncertainty persists. Might the upcoming radio opportunity yield more than quiet? Post-October 29th, 3I/Oumuamua vanishes behind solar glare, creating a tracking void for both terrestrial and Martian viewpoints. Over the ensuing 5 weeks, no observatory can monitor its whereabouts, luminosity, or structural changes. Such interruptions are routine around perihelion, imposed by solar interference and orbital safeguard measures. Through November, astronomers, enthusiasts, and searchers for technological markers alike monitor the timeline, anticipating mid-December when the interloper resurfaces before dawn. For primary observables await dominating the priority list are overall luminosity, path relative to fixed stars, tail or jet shape, and unique spectral signatures. Investigators will examine each for alterations. Has the body broken apart, dimmed, or altered its direction? The upcoming observation slot is short yet pivotal. Confirmation hinges on what appears after emerging from that solar occlusion and if the readings align with forecasts or amplify the enigma. Distinguishing genuine signals from interference starts with a straightforward hierarchy. At the foundation lies consistency. Authentic traits, such as streaks, bursts, or escorts, must show up across separate image sets, aligned by timestamps and orbital data from various groups. False positives, however, disappear when analysis methods or alignments are adjusted. Following that, validation across wavelengths. A legitimate entity ought to show in multiple bands or spectra, with color balances that align with physics. Spurious effects typically appear only in one range or alter hues with varying techniques. Higher up, positional and kinematic indicators. Real escorts should travel alongside, following expected orbits while keeping steady distances, without erratic shifts or smudges based on layering. The highest level involves intentional maneuvers or features, purposeful movement, targeted radio emissions, or recurring patterns. These are exceedingly tough for natural processes to mimic. Every assertion ascends this hierarchy, encountering tougher challenges at each stage. The level of required substantiation escalates with the boldness of the proposal. The tally remains public. Flag all irregularities, insist on solid proof, and allow the facts to decide. On the chemical front, 3 Challenger models for the I/Atlas comet. Its nickel-to-iron proportion, dominance of carbon dioxide, and enormous sunward ejecta all distinguish it. Still, the most vital proof stays hidden from general access. The trajectory projection intersects the site of the 1977 WOW signal with a mere 0.6% chance factor, though no separate radio observations have surfaced so far. As I/Atlas nears its closest solar approach and an observational gap, the evidence calls for careful scrutiny and restraint. Pending the following data drop, the puzzle persists. We face a cosmic conundrum, a pile of oddities, and 0 verified solutions. Just the data and our subsequent actions with it.